We'll briefly look at diodes and go over what a diode is, how it works and what it does, and how it changes the calculations in a circuit, okay? So hopefully remember that a diode only lets the electrical current flow in one direction, okay? So if it's in its forward bias position, it means electricity only goes through it in one direction and cannot go through it if it's in reverse bias. Now the symbol for a diode looks like that. Now, when we're pushing against the diode and we've got a potential difference across it, we can draw a graph of voltage against current. Now if we push our potential difference in the reverse bias direction, then no current will flow. So if we try and push a current through it in this direction, no current will flow. So we get no current. When it's in the forward bias direction, we put a potential difference across it, then a current will begin to flow. Now then, you'll notice it doesn't suddenly start flowing once we reach 0 volts. That's because it needs to reach this point here. Now this is called the threshold voltage. Now, the threshold voltage is normally equal to 0.6 volts. Now, depending upon the question, they might say to you it's 0.7 volts, it's 0.65 volts, but normally, as a rule, it's about 0.6 volts. So the diode takes 0.6 volts potential difference and then the current will flow through it. Now this is really important when it's in a circuit because you need to think of it as taking 0.6 volts before anything will flow through it. Up to 0.6 volts, it has an infinite resistance, if you like. But once you've gone past 0.6 volts, it will allow any current to flow through it. So an example, a very simple example might be this. Now normally, this is a very, very straightforward series circuit problem, and if somebody said, what is the current in this circuit? Now normally you would say, okay, the current I is V over R, which would be 3 over 4. But in this case it's slightly different because there's a diode in place. So we need to consider the diode. The first thing you must always do is think about, we've got 3 volts EMF, this has got 0 internal resistance. We've got 3 volts EMF. Now what's going to be lost across our components? And it always will be 0.6 volts across our diode. Now across the 4 ohm resistor, all that is left is 3, take away 0.6, so we'll have 2.4 volts across our 4 ohm resistor. So to work out the current, we would then simply say I is V over R, which is 4 over 2.4. Which is 1.67 amps. Okay, so that's how you'd work it out. Now it's not what you would normally think if you didn't consider the diode. Okay, now we could have it in more complex problems such as a parallel circuit. So if you saw it in a more complex problem, it might look like this. This is a 3 ohm resistor. 3. Now, they might ask you, what's the total current flowing in this circuit? So what's the current flowing there? Now normally, you would think of this as resistors in parallel. You would do 1 over RT is 1 over 4 plus 1 over 3. You'd make your common denominator 12, and you'd be able to solve what the total resistance of the circuit was, and then work out your current. Now in this problem here with a diode, you can't do that, because the potential difference changes, okay? Now, as long as we stick to our very, 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 very simple rules, this is a very straightforward problem to solve. We remember the potential difference across each branch is always the same in a parallel circuit. So the potential difference across this branch here is 6 volts, and the potential difference across this branch from here to here is also 6 volts. Now it's essential to remember the diode takes 0.6 volts. So if the diode takes 0.6 volts, what is left for the 3 ohm resistor? Obviously the EMF of the battery is 6 volts, so therefore we've got 6 take away 0.6, which is 5.4 volts. This 4 ohm resistor doesn't have anything else in series with it, so he gets all of the 6 volts. Now what's happened is the current flows from our battery, and when it gets to here it splits. Some goes down there and some goes through our forward bias diode. Now we need to realise how many amps go through here and how many amps come through here, and add them together to work out the current that flows back up through to the battery. Now then, this one here, we could call this A1, and we could call this branch A2. So for A1 we could say I is V over R, the voltage is 6, the resistance is 4, which is 1.5 amps. So we know we've got 1.5 amps flowing through this branch. Now this branch is slightly different because we've got a diode in place. So in this branch we could say A2, I equals V over R, which equals 5.4 volts over 3. And 5.4 over 3 equals 1.8 amps. So we've got 1.8 amps flowing through here and 1.5 amps flowing through here. Now both of these meet at this point here, so we've got 1.8 down there and 1.5 up here. So if we add them together, the total current that flows through the circuit, which will be the current through this ammeter here, is 1.5 plus 1.8, which is 3.3 amps. So we would say the total is 1.8 plus 1.5, which is 3.3 amps. So if we've got a problem with a diode in this parallel circuit, that's how you'd work it out. We could have other problems with diodes in parallel, with components, to protect components, but as long as we remember 0.6 volts, and once it reaches 0.6 volts, it draws no current at all, okay? Then we should be okay.